Hello everyone. Today I'm presenting distributed consistent semantic multi-robot localization and mapping. I am Vladimir Chuyev and I'm presenting this work of me with my advisor Vadim Mindelman. We present an approach for multi-robot distributed semantic SLAM, and within this approach we address classification is the key component in solving this problem. We address some key challenges within our approach. First of all is consistent estimation. We want to avoid double counting and we want to avoid overconfident estimations. The second is classification aliasing, where objects from different classes appear similar from multiple viewpoints and it causes uncertain classification estimations. Now present some related works to our problem. So first of all, many works in distributed systems do not address semantic information, as opposed to our work, which does address semantic information. And as a result, those many works all consider only double counting and consistent estimation within continuous random variables, while we, on the other hand, consider both continuous and discrete random variables. Works that do address classification, they use most likely semantic measurements. Those are pretty simple measurements, do not contain a lot of information, but on the other hand, we consider more informative vector of class probability measurements. And finally, we do eventually have to reason about hybrid belief. In a previous work, considered hybrid belief for a single robot, but on the other hand, we consider hybrid belief for distributed systems. And this leads us to our contribution. Our contribution is twofold. First of all, we maintained a multi-robot approach that maintains a hybrid belief over robot object and poses and object classes, and this approach also addresses the coupling between classification and localization results via viewpoint-dependent classifier model. And the second contribution is addressing estimation consistency. First of all, for a continuous random variable, and more importantly, with a contribution to discrete random variables. First, we address double counting, specifically for discrete random variables. As you well know, in distributed system, a measurement should be counted no more than once. The opposite can happen when information relates from other robots, and double counting may lead to overconfident estimation. Specifically for discrete random variables, consider the following example, which we have two sets of measurements, and the green measurements in here can be counted twice, but the red denominator keeps the posterior from containing double counting. Without this denominator, which can happen in classification problems, this measurement is double counted, and when it's double counted for discrete random variables, it pushes the class probabilities to the extreme. This will be especially problematic if the high class probability is for the wrong class. Let us go over some definitions. We aim to maintain a joint hybrid belief as follows, which X is all robot and object poses, C is the class realizations, H are measurement history up until time K. You can see here the superscript, the capital R. There can be superscript small r, which represents a single robot, and capital R, which represents all robots communicating with small r, including small r itself. The measurement history consists of both geometric and semantic measurements, as you can see in the drawing on the right, that every robot observes multiple objects. Each object gives the robot semantic measurements, seen as class probability vectors, and geometric measurements, we use here is relative pose. The assumptions that we use are, first of all, static environment, then we assume that data association is solved for us, and we use Gaussian model for the motion model, geometric model, and classifier model, in which we will go over in the next slide. To shorten notations, we use the likelihood notations, L, that combines both the geometric model and the classifier model. Our semantic measurements are considered here viewpoint dependent, as you can see on the figure on the left, which review the SUV for multiple viewpoints, and each and every viewpoint gives us a different probability vector. If we can model this relationship, we can use it to improve our localization and classification. We take a model that is assumed Gaussian with expectation and covariance that are both viewpoint dependent and class dependent. In reality, we train number of models as the number of classes, and this model allows us to reason between the coupling between classification and localization. Here we present our general approach, both for single and distributed systems. We take the hybrid belief and split it using the chain rule to continuous conditional belief in blue and the discrete belief in red. For a single robot, our incremental update is as follows. For the continuous, we use a standard SLAM-like approach, in which we use the likelihood and the motion model to forward the belief. The discrete weight, we use both the continuous and the discrete beliefs for previous time to update it, and we also marginalize over poses. And for the discrete incremental update, it looks similar, but in addition, we have update terms in dark blue for continuous and dark red for discrete that we add to our incremental update. Now the question is communication between robots. How do they communicate with each other, and what do they send, and how do they avoid double counting? So first of all, each robot performs a hybrid belief inference both for individual and joint beliefs. Each robot also maintains a stack of individual hybrid beliefs got sent to him by other robots. This stack is what is sent to other robots during communication, and this stack contains cell, each cell per every robot. It contains the marginal object poses and the marginal object classes, that in just taking the current beliefs and dividing them by the prior. And also contain a timestamp k of what is the latest timestamp the robot has received information. How does this stack look like and what is its size? For every R robots and objects with M kinetic classes, each stack contains m by the power of n multiplied by r marginal pose beliefs and marginal weights, and also our timestamps. In principle, it grows exponentially with the number of objects observed, but in practice, many beliefs have very small weights, or actually zero, and can be proved to reduce computational effort in larger environments, in future timestamps and such. On the right, on the diagram on the right, you can see how it looks like visually, which we can see each robot has its own stack that has information from other robots, and it communicates between each other. How do we maintain information consistency? Per each cell, the receiving robot compares between the timestamps that it has and the timestamps for the information that it receives. If it receives information with a newer timestamps, this corresponding slot is updated. And when we go to our previous approach outline, we can see that this is how the continuous terms and the discrete terms update. It just takes the old information and removes it using this division. And this division for continuous random variable can be done with, for example, by DDF-SAM2. This formulation avoids double counting by removing this old information for both continuous and discrete random variables. Now we present our experimental setup. We have a scenario with 3 robots communicating. Uh, each has its own graph truth trajectory, as you can see on the figure on the right, with different colors. We have 6 chairs in the environment with different orientations. We have 3 candidate classes, and we trained corresponding classifier models. We compare between 3 cases. The case where each robot maintains its own belief, a case in which the robots do a distributed inference but doesn't reason about double counting, and finally our approach in blue. We use for classification benchmark the MSDE benchmark, or a mean square displacement error, which is detailed as follows. On the bottom right, you can see some examples of the images with bounding boxes of the chairs that we were using. To present our results, we use 2 types of graphs. We have the slime graph and the classification graph. For slime graph notations, we have in colored path our ground truth path. We have in green the ground truth of object poses, and in black the object pose estimation plus covariance. We have in the red dot the ground truth pose for the robot, and the robot pose estimation covariance in red and blue. The current robot observation is shown in a gray line, and we also have a robot communication graph for the distributed case. For the class probability graph, we show it here with bar plots. For class 1, the bars are blue, for class 2 the bars are orange, and for class 3 the bars are white. This corresponds to all 3 candidate classes. The blue bars are actually the ground truth, so optimally we would like to see a bar graph that is colored entirely in blue. Now we present the experimental results for the case where the robots don't communicate between each other. This is divided by 3 columns, and from left to right this is robot 1 to 3. And you can see in the bottom row the classification, especially for robot 2, is not very accurate for some of the objects. Now in the second case, where the robots do communicate between each other, where we use a full algorithm, you can see that first of all, the estimation accuracy increases, the estimation covariance reduces, the coverage of each robot, the amount of object that it sees increases. You can see also that the classification accuracy increases with time and the communication between robots. And the classification scores are getting pretty much similar because the robots communicate between each other and the state gets closer between each other. Now we show graphs that were also presented in the paper. We compare between the cases where robots don't communicate between each other, where we do have double counting, and when our full algorithm is activated. So we compare localization accuracy in the first graphs. In the next, we present the measure for estimation covariance, and the third, we use a metric to show how much our classification results are accurate. We use the MSDE metric for that. To summarize our presentation here, we present an approach for multi-robot semantic SLAM. We did this by maintaining a hybrid belief over robot and object poses and object classes. We reasoned about the coupling between poses and classification via a viewpoint-dependent classifier model, and we avoided double counting both in continuous and discrete random variables. Thank you everyone for listening.